So it's a great pleasure to invite you all for this seminar today. It will be actually a colloquium, and which will be on fractons, and probably we have the best person to talk about it, who is Rahul Nandkishore from Colorado Boulder. And so over to you, Rahul.
Thanks for the invitation. I'm happy to tell you something about fractons. So yeah, so today's talk will be partly just an introduction to fractons and maybe explaining why it's of interest to people from many different backgrounds. And partly also I'll be trying to present like some of what I think is cool about fractons. Okay, so I'll sort of structure the talk as following. I'll start by explaining what are fractons. I'll then explain why they're interesting, and it ties into such basic questions like what is a phase? Do all phases have a low energy continuum field theory description? What phases could there be? I'll then discuss some of the new thermodynamic and in particular dynamic phases of matter that you can realize using fractons. And then I'll sort of conclude with some outlook. So what are fractons? Well, they're new sorts of phases of matter, originally discovered in 3 space dimensions, although by now we know how to get the essential physics in 1 and 2 dimensions as well. And the signature property is that the excitations exhibit fractionalized mobility, meaning that the elementary excitations are either totally immobile or able to move only in certain directions and not others under Hamiltonian dynamics, whereas composites of multiple elementary excitations can move freely through the system. So I should say at any point, if people have questions, just unmute and ask, please.
Yeah, so how do these differ from quasi-particles in some sense?
Well, so you can say that the fractons are the quasi-particles of the problem, but these are quasi-particles which have constraints on their mobility. And we'll see very shortly how those constraints come about.
So this is like different from, you have the charge and spin excitation separate from an electron in some sense.
Yeah, so let me maybe show an example. And
okay. I think I should hold my question.
Yeah, I mean, I'll show an example very shortly. So yeah, just a lightning history lesson. The first modern fracton model is probably written down by Chamon in 2005. And then condensed matter people didn't pay any attention whatsoever. The first people to pick up on it were from the quantum information community, people like Bravi and Ha and Yoshida. And then condensed matter people only started paying attention around 2015, 16. But in the past 5 years, maybe there's been a real explosion of interest, and this listing sort of stops in 2017, but there's sort of exponential growth in the number of condensed matter papers and fractons since then. And it's a topic that really connects to a lot of different areas of physics. So quantum information, I mentioned already, condensed matter, topological order, glassy dynamics, gauge theories and gravity, and sort of all of these different areas connect to the study of fractons. And as this intro goes on, I'll sort of explain how this topic connects to all of these different areas. But I think I should maybe actually give you a concrete example of what a fracton phase is and how it works, so you know what I'm talking about. Yeah. Was there a question?
Sorry, I just yeah, please go on, Rahul.
Okay, so it's always easiest to illustrate by example, and the simplest example I know of a fracton phase is a model that's called Xcube. Now, I should caution from the outset that this model is very baroque. It's not something you would expect to be a realistic model of any material. But the nice thing about this model is it's exactly solvable, so you can make exact statements and there's nothing to argue about. And furthermore, you can show that this model is a sort of fixed point Hamiltonian for a phase. So the sort of essential properties are robust to perturbations. So you can calculate a bunch of properties of the phase using this fixed point Hamiltonian. And then you can hope that you can expect that those properties would be common to any system that realized this phase, even if it was somewhere else in the basin of attraction. in parameter space, which was not actually this fixed point Hamiltonian, but had some other Hamiltonian, which was in the same phase. So you should think of it as analogous to the toric code model, right? So the toric code Hamiltonian is a exactly solvable Hamiltonian, which provides sort of fixed point Hamiltonian for sort of Z2 spin liquid. Yeah. Okay, so that's just like some background on how you should think about the Xcube model. So the Xcube model is a model that's defined on a cubic lattice. Now, on every link of the cubic lattice, you place a single spin half variable. And the Hamiltonian contains two sorts of terms. It contains A's and it contains B's. And the A operators are a product of 12 Pauli X operators on the 12 links that frame an elementary cube. And the B operators are, you pick a vertex, you pick a plane, either XY or XZ or YZ, and you take the 4 links that connect to that vertex and are in that plane, and you take the product of the 4 Z operators on those 4 vertices, and that makes the B's. And the Hamiltonian at the most bare bones level is the sum of all A's and the sum of all B's. Okay? And you can readily convince yourself that these A's and B's all commute with one another, which means you can simultaneously diagonalize all of them. And the ground state has eigenvalue +1 under every single A and B operator. Yeah? So this is the basic exactly solvable Hamiltonian. And now you could imagine perturbing it by kind of adding some fields or some any other local perturbation that you want to perturb with. Now, like one thing that you can readily verify if you sit down and count is that if you have open boundary conditions, then with open boundary conditions, the ground state is unique. And anytime the excited states have eigenvalue -1 under some of these operators, and you can straight away see that there is a gap to the excited states. Yeah. Which means that any properties of the ground state that you construct are going to be robust to weak perturbations, just because there's a gap to the excited states. Now, if you're with periodic boundary conditions and it's more delicate, then you do have a ground state degeneracy. But it turns out that even with periodic boundary conditions, the ground states, while they're degenerate, the different ground states are indistinguishable under local measurements. So there's so local operators have no matrix elements between the different ground states. Now, yeah, so the ground states satisfy all projectors. With open boundary conditions, there's a unique ground state. With periodic boundary conditions, actually, there's an enormous ground state degeneracy, and local operators have no matrix elements within the ground space. Now, okay, that's properties of the ground states, but maybe the most interesting aspect of this is the properties of the excitations. So now let's imagine we start with a system that's in the ground state, and now we act with a Pauli Z operator on a single link. Now that commutes with every A operator because the A operators are made up of, it commutes with every B operator because the B operators are made up of Z's. It commutes with every A operator that does not contain this link, but it anti-commutes with the 4 cube operators that contain this link. So remember, the A operators were product of X's around the links framing an elementary cube. So this single Z operator will anti-commute with this cube operator. It will anti-commute with this cube operator. It will anti-commute with this cube operator. It will anti-commute with this cube operator. So if we act with a single Z, we'll end up with 4 excited cubes. If we act with 2 Z's, then I have got 1 anti-commutation here and here, 1 anti-commutation here and here. And these 2 cubes have had 2 anti-commutations, so those will be happy again. And in general, if I act with a membrane of Z operators, then everywhere in the interior or along the edges, I will have had an even number of anti-commutations. So I'm back to the ground state. But on the corners, and this was supposed to be colored, I don't know why it's not showing us colored, but On the corners, there will be a single anti-commutation. So on each of the 4 corners of this membrane of Z operators, I will be left with a single unhappy cube. Yeah, so this cube will have eigenvalue -1. So now I've started with the ground state and I've acted with this membrane of Z operators, and I'm left with 4 unhappy cubes at the 4 corners of the membrane. And now if you stare at this, you can convince yourself that there's no local operation you can make which moves these individual cubes around. So if I act on this link, then this cube becomes happy, this cube becomes unhappy, but there's also 2 more cubes which are sort of lying on top of them, which share that link and which become unhappy. Yeah. So there's no way I can just move this one unhappy cube around without creating additional unhappy cubes. The only way to do that is to expand, contract, or otherwise deform this membrane, and that's a non-local operation. Yeah. So these 4 unhappy cubes, which are formed at the 4 corners of this rectangular membrane operator, these, you can think of the single unhappy cube as the elementary excitation of the problem, and this elementary excitation is immobile under arbitrary local perturbations. Questions about that? So that's a sort of basic or sort of simplest realization that I know of this fracton property, that you get elementary excitations which are immobile under local perturbations and therefore under local Hamiltonian dynamics.
So can I ask something? Is it existence of fractons is a general property of general stabilizer codes in higher dimensions, like in 3D? Or...
Yeah. So this is an example of a stabilizer code which you can write down, which has fractons. And there are other known examples of stabilizer codes which have fractons. Now the stabilizer code examples are all in 3D. Yeah. So we don't know how to write down stabilizer codes with fracton properties in dimensions 2 or 1. But as we'll see in due course, there are simpler ways of understanding where these weird properties are coming from, and armed with those insights, we'll be able to understand how you can get the essential physics in dimensions 2 or 1. But it's nice to start with stabilizer codes because they're exactly solvable, right? So I can make statements, and these are exact statements, so there's nothing to argue about.
Thank you.
Okay. So you can also consider a bound state of 2 fractons. Now you can act with a string of Z operators, and this bound state of 2 fractons can move freely, but it can only move freely in a plane. It cannot move sort of transverse to the plane. So that's an example of a subdimensional excitation, which can move freely in certain directions, but not in others. Now, there are other examples of stabilizer codes with fracton properties. Maybe the most famous is Hauscode. So Hauscode is much more complicated. I don't want to go into a ton of detail. It's also defined on a cubic lattice, but now there is 2 spin-half objects on every vertex of the cubic lattice. And the stabilizer operators are various complicated products of Pauli operators acting on these 2 spins. In Hauscode, the elementary sort of unhappy cubes are made at the corners of fractal fractal operators instead of rectangular membrane operators. And they're all immobile under local Hamiltonian dynamics. And it has the sort of interesting property that if you try to move them, then in the Xcube model, if you try and move one of these unhappy cubes, you end up creating additional excitations. So there's an energy cost to trying to move things with local perturbations, but the energy cost is constant in the Xcube model. In Hauscode, the energy cost actually grows with how far you try to move something. It grows as log R when you try to move things. So again, that comes from analysis of Hauscode, which is also exactly solvable, but Hauscode is complicated, and I don't want to go into it too much. In today's talk, the main thing I'd like you to take away from it is that there's this log R energy barrier growing with distance in Hauscode. And we'll come back to that later because that's actually has some interesting consequences. Okay, so here's my sort of very quick summary. Now the key point is that the sort of elementary excitations, which I'm calling fractons, they're created, they're not locally creatable, they're created. So with ordinary topological order, you would have excitations created at the ends of strings, but with fractons, they're created at the ends of some higher dimensional object. Could be either at the corners of a membrane operator or at the corners of some fractal dimension operator, yeah? But they're created at the sort of edges of some operator with dimension bigger than 1. And now you can think of that as leading to the funny properties, namely the immobility of the elementary excitations under local perturbations and local Hamiltonian dynamics. They have other funny properties. So, in the world of topological order, people like to talk about topological entanglement entropy or maybe non-local entanglement entropy. There's various ways to get this. Like maybe one nice way is the Kitaev-Fresco construction, where you construct a bunch of regions, you calculate the von Neumann entropy of each of them, and then you do some careful subtraction, and this careful subtraction subtracts off all the local contributions, and you're left with some intrinsically non-local contribution to the entanglement. You do this for topologically ordered phases, and you get this universal constant, which is the topological entanglement entropy. You can do an analogous calculation, and we did it for fracton phases. What you find is that there is indeed a non-local, sort of fundamentally non-local contribution that's left over. Yeah. So it smells a little bit like topological entanglement, but unlike topological entanglement, now it actually also depends on the geometry of the cut. So it's non-local, but it's sensitive to geometry. Okay, so that's a handful of weird properties about fractons. Now, why are they interesting? Well, I would say that maybe the most important reason why they're interesting is because they challenge our understanding of really basic questions. So as an example of really basic questions, what is a phase of matter? Do all phases have continuum, low energy, field theory descriptions? Like what phases actually are even allowed to exist, either in equilibrium or out of equilibrium? And I may not have time to address all of these, but sort of fractons have maybe provided counterexamples to a lot of things that we thought we knew, or we thought we knew the answers to most of these questions, and actually the study of fractons has provided counterexamples to a lot of things that we thought we knew. So, for instance, what is a phase? Well, standard definition might be that, well, it's a region of parameter space or a region of Hamiltonian space which has some sharp universal properties which are robust to perturbations. So if you were studying an Ising model, then the ferromagnet has a magnetization and the paramagnet does not. If you were studying the quantum Hall effect, then in the quantum Hall phase, you have a quantized Hall conductance, and that's your sharp universal property that's robust to perturbations, and so on. Yeah? So this is the colloquial understanding of what a phase of matter is, and there's two classic ways to formalize it. One is by the notion of adiabatic continuity. So now you have a solvable Hamiltonian, which has some property, and then you argue that you can perturb about this Hamiltonian, and this property survives. You have some sort of adiabatic continuity to the solvable Hamiltonian. The other way to think about it is you could think of phases as stable RG fixed points. So you imagine doing some renormalization group procedure on long wavelengths, you flow to some fixed point. The low energy properties are captured by some effective continuum field theory, and sort of every phase corresponds to some stable fixed point. So these are sort of two classic ways to think about phases. Are they actually equivalent?
Rahul, can I ask some question here at this stage?
Yeah.
Perhaps it's a stupid question also. So if you have if you have a translation symmetry in the system, so there exists a momentum operator which one can use to move operators. So is this true? So in that case, the momentum will not be a local operator. It's not integral of a local operator.
Yeah. So the fractons are not eigenstates of momentum. Yeah. And every time, every state with a particular distribution of fractons is in its own superselection sector. So yes, it's sort of formally true that you have translation symmetry, but translations actually change which superselection sector you're in.
Okay, so but what would be the action of a translation operator on this? So is this a well-defined notion? So if I take a commutator of the momentum, with a fraction operator, which is localized somewhere, what should I get?
I mean, you'll get if you take a commutator of I guess the problem, well, if you just take the state and you act on it with translation, you'll get the state with the fractons moved over by 1 unit, but now that's in a different superselection sector. I mean, maybe actually the way I want to answer this question is, we will see later on in this talk that you can think of the funny fracton properties as coming about because of emergent conservation laws on multipole moments of charge. Multipole, so like charge is conserved and say dipole moment is also conserved. And it's these.
I see. So basically, so these charges do not commute with the
exactly.
translation.
So
is that so?
Multipolar symmetries do not commute with translation.
So you are in some kind of super selection sector, and basically then the translation would be an illegal operation because it takes
exactly
because you don't allow for okay. Nice. Yes. Thanks.
Okay, so to come back to fractons and the meaning of phases, Xcube, which I showed you, it's a phase in terms of adiabatic continuity. So you define it with open boundary conditions. Let's say it has a unique ground state. It has a gap to the excited state, so you can perturb it, and the ground state should be robust. Now, this is sort of classic definition of adiabatic continuity. At the same time, if you do it with periodic boundary conditions, the ground state degeneracy, ground state degeneracy is a universal low energy property, but it's exquisitely sensitive to system size. It's exponential in system size. So how could you possibly capture this in any sort of continuum field theory description, which has forgotten about the UV regularization? Or topological entanglement entropy, that's a universal low energy property. But the topological entanglement entropy for fracton phases, it knows about lattice scale. It knows about the size of the entanglement cut. So again, how could you possibly capture that in any sort of continuum field, like purely continuum field theory, which has forgotten about the UV regularization? In any sort of field theoretic description of fracton phases, or sort of RG fixed point type description of fracton phases, is going to need to retain some information about how the theory was regulated in the UV. So you can call this UV IR mixing if you like, but it's certainly not the sort of standard picture we have of RG fixed points, where you've essentially forgotten all about the UV entirely, and all you've retained in your description is stuff like dimensionality and symmetries and so forth. So in that sense, they don't really fit into the sort of familiar picture of phases as sort of RG fixed points with some plain continuum field theory description that's insensitive to the UV. I also mentioned that, fracton in one location is in a different superselection sector to a fracton in a different location. So like in some sense, the number of particle types is proportional to volume, which again, is very non-standard. That's not something that usually happens in phases we're used to thinking about.
Can I ask something?
Yeah.
So I would like to know, so the fractons, what are the statistical properties of these fractons?
Yeah, very good. So I mean, the fractons themselves, of course, they're not mobile, right? So you can't, it's hard to envision doing a braiding operation where you drag one fracton around another. But you have these subdimensional particles which can maybe move in certain directions and not others, and you could imagine doing things like braids with them. Or more generally, you could say that instead of talking about grading, you could sort of talk about remote detection, right? Because that's what statistics really is about. Can you do something that stays far away from the particle at all times and still infer something about the particle's presence? So this is worked out in a nice paper by my colleague Mike Hermele. So you can do remote detection with fractons. It depends on what model you're talking about, but you usually end up with sort of bosons or fermions or semions maybe sometimes. I think in most of the stabilizer code models, the excitations are either like bosons or fermions or semions.
Okay, so as a follow-up, so it means the statistics operator is not like super selected in these theories.
I'm not sure I know what that means.
I mean, it's because, I mean, if you take any field theory, the statistics operator is super selected. So you have a well-defined idea of what bosons and fermions are.
Right.
So if you have QBIR mixing, I mean, if there's a theory with possible QBIR mixing, it could be that the statistics operator is not properly super selected. So I mean, so such things also happen in non-commutative like field theories. So if you quantize the field properly, taking into account the statistics, then it's possible to eliminate this QBIR mixing, as it happened in something called twisted non-commutative field theories. I'm just wondering if you can do it in a discrete way and see it in these fracton fields also, but maybe, I don't know.
That's not something I know about. So, I mean, it's possible that there's a way to do this, but I don't know about it.
Okay, thank you.
So there's various properties that are difficult to reconcile with continuum QFT descriptions. Now, as we already discussed, the fact that translation changes the superselection sector means you can't really talk about momentum space. Again, we like thinking of continuum field theories in momentum space, but now momentum space is gone right from the beginning. But nonetheless, that we have made partial progress. So the key idea is this idea of symmetric tensor gauge theories, which was introduced by my former postdoc, Mike Pertko, later extended also to multiple gauge theories by Gromov. So how does this work? Well, if you have a familiar gauge theory like electromagnetism, then you have a Gauss law constraint, dV is rho, and this constraint implies a conservation law. So if you look at the charge in a volume, you can use Gauss's law to rewrite this as volume integral of div E, and now you can use the divergence theorem to rewrite this as a surface integral. And if the electric field is fixed on the boundary, then the charge enclosed by that boundary must also be conserved. So, so far so good. We know this very well. Normal gauge theories are written in terms of vector gauge fields. What if instead we wrote down a gauge theory in terms of higher rank tensor gauge fields? But I want to emphasize that these will be gauge theories of symmetric tensors. So this is not higher forms, which would be anti-symmetric tensors. Instead, this is symmetric tensor gauge theories. So let's say we consider gauge theory involving symmetric tensor fields. Rank 2 is sufficient. We'll work on the continuum, although implicitly there's still a regularizing lattice. And let's say it's a U1 gauge theory for maximum simplicity. Now the generalized Gauss law constraint should look something like this. Yeah. So now the electric field is a 2-index object, and just to make the indices match, I better have 2 derivatives. And if I have this sort of generalized Gauss law, then in addition to charge conservation, it also encodes an additional conservation law. So if I take the dipole moment in a volume, so just position-weighted charge density, I can use Gauss's law to rewrite this as a position times double derivative of electric field. Now I can use an integration by parts to get rid of the x, and now I'm left with single divergence of electric field. But now I can use divergence theorem and say that if the electric field is fixed on the boundary, or if my theory is defined on the manifold with no boundary, then in fact, now this dipole moment must also be conserved. Yeah? So this theory should conserve not only charge, but it should also conserve dipole moment. And that gives a very natural and intuitive way to get this sort of signature Fracton property. So if you have a charge sitting here, and you demand that the dipole moment of the theory must be conserved, then the charge cannot hop either left or right. Because if the charge hops, then the dipole moment will change. Yeah? And now essentially what you'll get is your theory will break up into different symmetry sectors labeled by dipole moment. Yeah? And acting with the translation operator, which I previously said, well, it changes your superselection sector. The way that gets implemented is acting with the translation operator. It actually changes your dipole symmetry sector. Yeah. Translation doesn't conserve dipole, and sort of acting with translation, it changes which dipole symmetry sector you're in, whereas actual quantum dynamics must always be diagonal by symmetry sector. Yeah. How you do this with the sort of type 2 models like Hauscode is a little more complicated, but there is a way to do it. Essentially, you sort of generalize to multipolar theories. So you demand that your yeah.
Can I ask?
Maybe this is kind of stupid, but
Sure. Please interrupt and ask here.
So the question I want to ask is these additional conservation laws, as well as the fact that the charge should be conserved, as well as the dipole moment should be conserved. The way you will write it into a field theory is by putting some sort of a constraint into your field theory. How do you incorporate this into an effective field theory? Because that's at least how I've learned to think about things.
Yeah, you can think of it as an emergent constraint.
It's an emergent constraint. So the constraint probably is put in as some sort of a Lagrange multiplier sort of thing in the field theory.
Oh,
some sort of Gauss field sort of thing.
So I would actually prefer to say, okay, so I don't want to impose this constraint. Well, okay, let's decide what game we're playing. So there's multiple games we could be playing. One is you start with some model of, I don't know, frustrated magnetism, and you want to get this as the emergent low energy field theory. Yeah. So in that case, I wouldn't want to put this constraint in by hand, which is what I would be doing if I did Lagrange multipliers. Instead, I would hope that somehow the effective low energy theory somehow automatically generates this constraint. Yeah. Now the other game that I could play is, and which I'll talk much more about later on, is we could say, well, okay, let's it's this dipole conservation property that really gives rise to the key fractonic properties. So let's consider a theory which has dipole conservation built in from the beginning. And let's just study the properties of this theory with a dipole conservation law. Yeah. So there it's simplest to just do it at the level of a Hamiltonian. So you write down a Hamiltonian which commutes with the right thing.
Okay. Right. Thanks.
Yeah. So again, I want to emphasize that this is still implicitly very much formulated on the lattice. So we're saying that dipole moment is conserved, but dipole moment is quantized because we're on the lattice. So it's sort of charge times lattice constant.
Right.
Yeah. And if we were not on the lattice, then you would have sort of continuously varying dipole moment, and we don't want that.
Can I also have some related questions? So in the original models, there are non-local operators that can move fractons, right? I mean, although you cannot, but in the field theory, there is nothing. But you would expect that even in the low energy description, there has to be such operators, right?
No, but I mean, those operators are not in the Hamiltonian, right? The Hamiltonian just contains local stuff. The non-local operator that goes down is just, I could imagine, as some omnipotent experimentalist, I could imagine coming in and acting with this non-local operator and ask what this does.
Yes, but in the quantized low energy theory, you should have such
Yeah.
non-local operators also, right?
Right. Well, I would say, the usual rules of the game for doing many-body theory is you say that you only allow yourself to write down local Hamiltonians. Yeah. So in principle, you could write down such non-local operators, but I will declare that you cannot write down those you cannot write down anything like that, because you're only allowed to write down a local Hamiltonian or a local Lagrangian.
Yeah, but in gauge series, we do have non-local operators like Wilson loops, and which are, would you expect some similar stuff to build out
so
of it?
you're thinking of Wilson loops or something like that, right? But
yeah, I was thinking if there are some
usually,
operators that you could construct.
But that's a test operator that you insert, right? So you insert some test Wilson loop operator and then see how the system behaves. But if you write down the Lagrangian of QED or QCD or whatever, it doesn't have anything non-local in it, right?
Yeah, that's true. Yeah, but I was thinking of whether in the low energy description itself, we could construct such non-local operators which can take you from one sector to, I mean, because the main puzzle is in this super selection sector, how to think of it from the point of view of the field theory. That's what Raj was asking. So I was thinking whether it's only the super selection sector is only seen by local operators.
Yes, that's
it
right.
can be,
yes.
or it is.
You could construct non-local operators, which would, and there are no super selection constraints with respect to non-local operators.
Okay, I see. Thanks.
Okay, so that was one reason why fractons are interesting, and sort of challenge our understanding of phases of matter. They also provide a new setting to do condensed matter physics, and sort of leads to discovery of new phenomena. And maybe in the rest of the talk, I could tell you a little about some of that, and specifically, I can tell you maybe a little bit about the quantum dynamics of fracton phases at finite energy density. So, fractons have restricted mobility. If you just put down a state where you have a vanishing density of fractons, and those fractons cannot move at all, so now you could write down a Hamiltonian which is nominally translation invariant, but which will nonetheless be localized, and that you'll have excitations which don't move at all. Really, that's just because each excitation is in its own superselection sector. The less trivial version of this is you consider excitations which are present at non-zero density. Yeah? Because if they're present at non-zero density, then you have precisely this issue that you can do non-local things whereby the excitations move in some correlated fashion. Yeah? And they could move in some correlated fashion, which preserves the dipole moment or sort of otherwise preserves the symmetry sector. Yeah? So even if you write down a Hamiltonian which has only local terms and you do local perturbations, yeah, then to leading order, you've got only local perturbations, but now if you start doing higher order perturbation theory, you'll generate terms that are more and more non-local, right? If you go to order n in perturbation theory, you'll typically generate operators that have range n. And you might think that if you have some finite density of excitations, then maybe they can start making correlated moves and start exhibiting non-trivial relaxation at some finite order in perturbation theory, and therefore at some finite timescale. Yeah. So we studied this in this paper. I'll actually maybe skip the details, sort of studied it with various methods drawn from the study of many-body localization. The bottom line was that you get you get very slow equilibration, but you do get equilibration. And the time scale on which the system equilibrates, and now this is for the exactly solvable models, the time scales on which they equilibrate is, for Hauscode, for instance, it's super exponentially long. So it goes like exponential in 1 over t squared, where t is temperature. So the equilibration time scale diverges very rapidly as you go to 0 temperature. But at the end of the day, it's still some finite time scale at any non-zero temperature. But that's that's with the stabilizer code models. The stabilizer code models have the property that they are all so you can think of them in terms of they have charge and dipole type conservation laws, but they're just discrete conservation laws. So you conserve Z2 charge and maybe Z2 dipole. And I sort of skipped the details of this part of the talk because this is not the most interesting, and I want to be sure I have time to get to the most interesting results. And the really interesting results come when you promote from Z2 type conservation laws to U1 type conservation laws. And when you do this, you find something really new. So I'll give a quick recap of Anderson localization. So the conventional Anderson localization requires strong disorder. It also requires energy conservation. So there should be no noise in the problem. Whereas what we found is that by sort of borrowing insights from the study of fractons, we now know how you could get localization and translation in invariant models and in models with noise, so there's no energy conservation. And the results are absolutely rigorous, and now you can prove things, there's nothing to argue about, but they require what I call fractonic conservation laws. In particular, you need conservation of both charge and dipole moment, which looks extremely artificial, but actually this has,
Ask a quick question
yes.
about NDL physics.
Yes.
So, what sort of analysis do you do? I mean, are you working with an effective Hamiltonian that only looks at the fractons and then do some sort of exact diagonalization? How do you get these? And I could of course read your paper, but
are you talking about the results I was presenting before on the stabilizer code models?
Yes, exactly, absolutely.
So those are mostly based on you try to construct some approximate locator expansion, and the locator expansion breaks at some order in perturbation theory, and you estimate the matrix element for the order in perturbation theory at which the locator expansion breaks, and that gives your effective timescale. Yeah, so now these U1 models, and they look very artificial, but as we'll see, they actually have multiple natural experimental realizations, simplest being ultra-cold atoms that are tilted potential. So the basic setting is we want charge and dipole conservation, and general rule of physics, everything should be made as simple as possible. So let's go all the way down to one dimension, and we'll consider a one-dimensional problem with charge and dipole conservation. And the simplest realization, simplest non-trivial realization is you have a spin one chain. So like 1D chain, on every site, there's a single three-state degree of freedom, a single spin one, which can be +1, 0, or -1. The conserved charge is the z component of the spin, +1, 0, or -1. And the dipole moment is defined in the obvious way, position weighted charge. And we're going to demand that both the charge and the dipole moment be conserved. Now you can straight away see that individual charges are immobile, because if you move a single charge, that will change the dipole moment, and you're not allowed to change the dipole moment. However, if you have a dipole, so a plus charge and a minus charge close together, those can move about freely. And also you can have this sort of process, which you could interpret either as a charge hops right and emits a plus minus dipole to the left, or charge hops left and emits a minus plus dipole to the right. Okay? And we'd like to consider quantum dynamics that's sort of minimally structured. The only structure we want to impose is that it conserves charge, it conserves dipole, and it is locally generated. Okay? So the simplest way to implement this is with a quantum circuit model. So you have some state, and then you generate the dynamics by acting with some operators, and each of these operators is compact in space, so that builds in spatial locality from the beginning, and each of these operators is also constrained to conserve both charge and dipole moment. If you're not used to thinking of quantum circuit models, then you can think instead, you can think of this as a sort of effective Suzuki-Trotter decomposition of some Hamiltonian time evolution. Again, essentially the same thing, but this is a nice explicit way of building in charge conservation, dipole conservation, and spatial locality. And those are the only constraints we put in. Yeah, so you act with these gates. Each of these gates is block diagonal by symmetry sector, but within each symmetry sector, you assume it's just a random matrix. Okay? And I build the quantum dynamics out of these gates. These gates can be chosen randomly in time, so there's no energy conservation. Now, if you want to make things maximally dramatic, you can choose them uniformly in space. So there is translation invariance. And what do you get? Well, we have a problem of sort of stochastic noisy dynamics. We might expect that you would get ergodicity. What might ergodicity look like? Well, quantum dynamics is always diagonal by symmetry sector. So you would expect that ergodicity means that the system fully explores all of the states in a given charge and dipole symmetry sector. So you might think the long time average state would look something like an equal weight superposition over all states in a given charge and dipole symmetry sector. And what I've shown on the left in these two plots is the charge density distribution in such an equal weight superposition. And as you can see, it looks essentially flat, yeah, as a function of position. Now on the right, what I've shown is you start with the charge sitting on a particular site, let's say site number 4, and then you just do this dynamics and you see where the charge ends up at late times. And you can see straight away that it looks very different. It looks like the charge remains localized close to where you started it off. So what's going on? In fact, for this minimal model that I gave you, charges are localized for in almost any state. Right? Essentially, the whole Hilbert space is localized, and ergodicity is broken for almost any initial condition. If you consider longer range gates, then typical initial conditions thermalize, but there's still a subspace that's exponentially large in system size within which ergodicity is broken. And it cannot be conventional localization because there's no energy conservation and there's no disorder. So what is going on? So that we explained in this other paper here, and I'll share that with you now. And again, there's a nice constructive argument which can be shown pictorially. So remember, we're considering a state, we're considering a quantum dynamics that conserves charge, it conserves dipole, and it is locally generated. So now let's consider a state that looks something like the following. It's all plus, then all minus, then all plus, then all minus. So it consists of all plus and all minus regions that alternate. And there's domain walls of the boundaries. And we're considering a state where the domain walls are at least as far apart as the biggest gates. Yeah. So the dynamics is locally generated. It's generated by local operators. And whatever the biggest of the local operators is, the domain walls are further apart than that. So now let's consider the dynamics of this state. Now, every gate or every operator acts across either 0 or 1 domain walls by construction. It can never act across 2 domain walls because the domain walls are too far apart. If it acts across 0 domain walls, then it acts on a state that's locally extremal charge. Nothing you can do to that consistent with charge conservation. If it acts across 1 domain wall, it acts on a state that's locally extremal dipole, given its charge. Nothing you can do to that consistent with dipole conservation, which means that this state must be an exact eigenstate of any quantum dynamics which conserves charge, dipole, and is spatially locally generated on the range M. Now, how many states like this are there? Well, you can take your system, you can carve it up into blocks of size M, and each such block you can allow to be either all plus or all minus. So this gives you a number of states, which is exponential in system size, and each one of these states must be an exact eigenstate of any quantum dynamics that has these 2 conservation laws plus spatial locality, whereas you only have polynomially many symmetry sectors. So there's the proof of ergodicity right there. Yes, that's a question.
Rahul, is it audible?
Yes.
Yeah, in this quantum circuit, all these behaviors are visible. Why are you only considering unitary operators acting on 3 sides? Means three particles. Can't we observe it? Two particles.
That's just the simplest non-trivial implementation.
Two. How about two particles?
If you did two particles, then every gate would be diagonal. So there's nothing non-trivial you can do with only two side gates,
Okay.
which conserves both charge and dipole.
Okay. Okay.
Okay, so sort of here's an explicit construction. Look, there's a number of states which is exponential in system size, and each of these states is just a product state on the computational basis, and it's also an exact eigenstate of the dynamics. So time evolution is always generated by a unitary matrix. The unitary matrix is always block diagonal by symmetry sector. The number of symmetry sectors is polynomial in system size, but there's exponentially many states, which are eigenstates. So in fact, the unitary matrix must contain exponentially many 1-by-1 subblocks, which means that essentially every symmetry subblock must further block diagonalize, and at a minimum, it must contain exponentially many 1-by-1 subblocks, which are these exact eigenstates. In fact, if you plot it in detail, what you see is that there's the full distribution. So each symmetry sector, it has all of these 1-by-1 subblocks, which are the exact eigenstates. It has 2-by-2 subblocks, so those are pairs of states that mix with each other, 3-by-3, 4-by-4, all the way up to subblocks with size that diverges in the thermodynamic limit. So you have this massive, we call it shattering of the Hilbert space, where the unitary matrix is not just block diagonal by symmetry sector, but within each symmetry sector, it further block diagonalizes into exponentially many subblocks with a broad distribution of sizes. All of this generalizes to higher dimensions as well. So if you were in 2D, you could conserve charge and then both components of dipole, x and y. If you just considered stripe-like states, then those are eigenstates by the argument I just gave. But you can also allow the stripes to roughen, and you can play this game first in the x direction and then the y direction. And this thing I've shown in figure C, this is still an eigenstate. You count the number of states of roughened stripes, and you see that there's exponential in area localized states in 2 dimensions. And the argument extends to arbitrary dimensions. It's just dimensional reduction. If you're in d dimensions and you conserve both charge and all d components of dipole, then you get a localized subspace, which is exponential in system volume. You can get even richer patterns with if you impose conservation of higher multiple moments as well. Now, you might think that conservation of charge and dipole moment is really baroque and weird, and on some level it is, but it's actually really easy to get an experiment. The simplest implementation is to consider ultra-cold atoms in a tilted potential. So the potential tilt couples to center of mass, and up to some pre-thermal timescale, you get center of mass conservation, and center of mass is just like dipole. So you might think that if you put cold atoms in a strongly tilted potential, then you would get effective conservation of dipole moment or center of mass of the cold atoms. And now you could see this sort of interesting physics where you have this strong ergodicity breaking, and the signature result essentially is that you have this exquisite sensitivity to initial conditions, where you pick a particular initial condition, which is one of these eigenstates, and it has no dynamics, and you pick a slightly different initial condition, and it relaxes very rapidly because instead it belongs to a big subsector of the unitary matrix instead. So this has in fact already been observed by 2 different experimental groups. There's also other realizations that we've proposed. There may be still others that we haven't even thought of yet. So to summarize this part of it, if you have just discrete conservation laws, then you're stuck with classic dynamics. Once you promote to U1 conservation laws, then you get localization, and there's a breakup of Hilbert space. It does require that the dynamics is strictly local. And it can be realized from a pre-thermal sense in various experimental platforms. Now, I said already that the time evolution matrix block diagonalizes within each symmetry sector. So far, I was focusing on these small symmetry sectors like these exact eigenstates, but there's also large symmetry sectors. There's these subsectors that diverge in size in the thermodynamic limit. The dynamics in these large subsectors is in fact thermal, but it's not thermal with respect to, it's thermal in a modified sense, meaning that you have ergodicity with respect to the subsector. So you end up exploring all of the states in that subsector. You can still ask, okay, suppose I pick an initial condition, which is in one of these large subsectors. What does the approach to equilibrium look like? Now, the canonical way to study approach to equilibrium is hydrodynamics. And the usual long-time behavior with hydrodynamics is diffusion. So here's the diffusion equation. And as we know, the diffusion equation has this characteristic relationship between length scales and time scales, where the length scale goes like the square root of the time scale. But in this fracton problem, well, you should still expect some kind of hydrodynamics to apply because we've got conserved quantities. But it's not diffusion anymore. Instead, what you find is subdiffusion, which we explained in this paper here. And the easy way to see this is that, look, the elementary mobile excitations are dipoles. And dipoles don't feel any force in uniform field. So the conductivity of the system must vanish. And if you're thermalizing, then there's an Einstein relation. And so conductivity vanishing means that the diffusion constant must vanish also. So the approach to thermal equilibrium must be slower than diffusion. And you can get a little more quantitative. Now, the dipole current is this 2-index object, Jij. So the generalized continuity equation should look something like this. In principle, you can derive this from Schwinger-Keldysh if you didn't want to just guess it. So now the question becomes, how is Jij related to the charge density? So you can get that with sort of standard thermodynamics. And essentially, it's related to two derivatives of the charge density. So you put it all together and you conclude that the analog of the diffusion equation involves the square of the Laplacian, or more generally, if you conserve the first n multiple moments, then you get a generalized diffusion equation, which looks something like this, and it involves n plus 1 powers of the Laplacian. And now just dimensional analysis tells you that you have a different relationship between length scales and time scales. Now length scale goes like time scale to a much smaller power, so it's subdiffusive, and there's an infinite family of subdiffusive hydrodynamic universality classes that you can access in this way, essentially by sort of tuning how many multiple moments you demand that your dynamics conserves.
Rahul, I want to ask something here. So, these charges are actually not moving because the fractons are not moving. So,
no. If you have a single charge, now if you have a single charge, it cannot move. If you have two charges, they can move in correlated fashion. So if you have one charge,
okay. So this is coming because of this. Right. I see. So then I had the follow-up question I have is is there some intermediate kinetic theory like picture one can give to understand this subdiffusion?
I mean, this is a sort of hydrodynamic picture which gives subdiffusion. Is there a kinetic theory? There is. I mean, if you want to do a kinetic theory, you need to now write down an explicit model, right? So that's in an older paper that I wrote with Sagar Vijay and Jason Yakonis, where we wrote down sort of models on the lattice that had these conservation laws. And then you sort of explicitly write down detailed balance equations, and you solve the detailed balance equations, and sort of this k to the fourth subdiffusion pops out. So that's a much more sort of microscopic kinetic theory type derivation. But then later we came up with this much slicker hydrodynamic argument, which tells you essentially without any reference to microscopics why it must be subdiffusion. Yeah. So I didn't put that paper slide, but it's Jason Yakonis, Sagar Vijay, myself from 2019.
Yeah, I just wanted to get some intuition about the mechanism of this of the subdiffusion, because usually in normal diffusion it's like Brownian transport, and here it's like
so the way to do it is you write down some model where you go to some lattice, you write down charge and dipole conserving moves, then you write down sort of detailed balance, sort of master equations for your probability densities, and now you go solve those master equations, and you'll get subdiffusion that way also.
Thanks.
Okay, so I think maybe my hour is up, so I should wrap up. So fractons are a new class of quantum states of matter. The key property is that the elementary excitations exhibit restricted mobility. They challenge many of our existing paradigms, how we think about phases of matter, things we thought we knew, and you can get qualitatively new types of behavior in the fractonic regime. For instance, they give you this new way of breaking ergodicity, which is robust to noise. It doesn't require disorder. It applies in arbitrary dimensions. It can give you these new hydrodynamic universality classes. And this is just sort of two that I picked because I like them. There's other new things that we found with the study of fractons as well. And it's sort of very much, I think we're still just at the tip of the iceberg with new stuff that we can learn by studying fractons and sort of things inspired by fractons. Yeah, a lot of questions are still open. There's theory questions. Is there a sort of modified RG perspective for explaining fractons? How far can we get with field theories? What other dynamic or thermodynamic phases might there be? There's also experimental questions. At some point, I had as an open question, how would we recognize a fracton phase? Like if you had some lump of rock which realized a fracton phase, that I think we actually know the answer to now. We have a fairly crisp spectroscopic diagnostics of fracton phases. But there's still the question of, well, where might we actually expect to get these sorts of phases in some sort of naturally occurring solid state system? We don't have a great answer to that yet, but it's certainly an interesting question to think about. And with that, I think I should conclude. I should thank various people that were involved as collaborators at various stages. I think 4 in particular deserve mention. So this is Abhinav Prem, my first student, now postdoc at Princeton. This is Mike Kretko, my former postdoc, now at the DoD. This is Vedika Khemani at Stanford, and this is Andy Lucas, my colleague at Boulder. And that I will conclude. Happy to take more questions.
Thanks for this amazing colloquium, Rahul. And yes, we should have more questions now.
Can I ask a really very stupid question? So there is this duality which you just talked about, right? There's this elastic theory and there's the defective elastic theory.
Yeah.
So is there an equivalent of the dynamic theory told for the fracton in the dual theory?
I can't really make out what you said.
So is there an equivalent of the dynamics that you have told for the fracton?
Yeah, sure there is. Yeah. I mean, the dynamic equivalent is that disclinations and dislocations don't move very easily.
Okay, the movement of these things, right?
Yeah.
But do they also perform this correlated movement that we see in the fracton?
Yeah. So I think single disclinations will be immobile, but if you have a pair of disclinations, you can bind it into a dislocation, and a dislocation will be able to move in certain directions, but not others. So you can make a full dictionary between these dynamical properties of fractons and dynamical properties of disclinations and dislocations in elasticity theory.
A nice experimental test bed with real materials with distillation.
Can you type? I mean, your voice is coming through very scrambled, so I can't make out what you're saying.
So, so all I'm asking is that wouldn't that be a very good test bed?
I mean, on some level, yes. I mean, the one aspect of it, which, I mean, so supposing I wanted to play devil's advocate. If I wanted to play devil's advocate, I could say, look, we already knew about elasticity theory, right? We've known about elasticity theory for decades.
Right.
So this is stuff we already knew, dressed up in new ways.
Right.
But yes, absolutely. I mean, I mean, I suppose ideally what you would like is you would like from this duality to fractons, you would like to come up with some sort of qualitatively new prediction for elasticity theory that you could then go and check in some experiment, right? So I don't know if we've really learned something new about elasticity theory yet from the study of fractals.
I have a question. This is Yasser here. Hi, Rahul. So my question is that in the context of quantum spin liquids, or rather classical spin liquids, where there's prediction of fractons in certain spin models, Heisenberg models, for example, higher rank Coulomb spin liquids in particular, do you think they admit a fermionic partonic description to describe the low energy properties, or as a variational description of their ground state wave function? In terms of Abrikosov pseudo-fermion, any other parton scheme?
I've never really thought about it. So I don't have an informed opinion on the topic.
Okay.
My instinctive answer would be, probably yes. If you're clever enough, you can find some, parton description. But that's not a direction that I've really pursued.
Okay. Thanks.
Deepak?
Yeah. There is some raised hand. Okay, please go ahead, Deepak.
Yeah, hi. Am I audible?
Yes.
Okay. So, hi, Rahul. My question is that when we think of gauge fields, right? We use them for parallel transport, right? They define holonomies. So for vector gauge fields, they parallel transport point particles. And rank 2 tensor fields or antisymmetric gauge fields, they parallel transport higher dimensional objects, strings. Am I correct in that? I believe that is the physical interpretation of what a high rank gauge field is. They correspond to parallel transport or holonomies of higher dimensional objects. I don't know if you knew about that description.
No, I can't claim to be familiar with this way of talking about the problem, but one thing that I do want to clarify is we're talking about symmetric tensors, not antisymmetric. So this is not higher forms.
Okay, fine. But I mean, but these are high. Okay, all right. So maybe there is a difference because of that. All right. And my second question, I guess, would be that when we have ordinary charge particles, right? We have phenomena like Landau levels, and when they couple to magnetic fields. So in this case, your excitations are again point particles. So they should also, is there some kind of similar behavior when they couple to these gauge fields?
Yeah, sure. And you would think that there's this sort of vast zoo of, let's say, thermodynamic phases that you could explore by taking these particles at finite density and symmetry breaking phases, topologically ordered phases. And I would say all of that is still very ill explored.
No, I mean, like if you just want to couple a point particle to a gauge field, right? You take the momentum and you add a p plus a term to that.
You can do minimal coupling.
But in this case, fractons don't have, individual point particles don't have kinetic terms, right?
So at the level of a Hamiltonian, you cannot write down a single particle hopping term, right? So you cannot write down b dagger I, bi plus 1. But you could write down B dagger I, Bi plus 1, Bi plus 2, B dagger I plus 3. Yeah, so that's a
Right.
correlated hop of 2 particles. That's
Right.
fine. Or, so you could also ask, if I were trying to write down some sort of Lagrangian description, right? Like, what's the right way to do it? So if you want to write down some Lagrangian description, you want to build in charge and dipole conservation from the get-go. You want to write down then an action, which, the action is in terms of maybe some scalar field phi, and you want the action to be invariant under phi goes to phi plus constant, so that's charge conservation. But you also want it to be invariant under phi goes to phi plus constant plus lambda x, so that's dipole conservation, sort of lambda is any. Yeah. So what that tells you is that your action cannot contain grad phi. It can only contain the Laplacian of phi.
Right.
So instead of having grad phi squared, your kinetic term will now look like Laplacian of phi squared.
Laplacian phi squared. Okay.
And
So-
equivalently,
so-
if you took this sort of 4 boson correlated hopping term that I talked about,
Yeah.
and if you rewrote this in terms of sort of density phase representation, and you took the long wavelength limit, again, that would give you something like Laplacian phi squared.
So once you do that, can you then go ahead and write down some sort of minimal coupling?
Yes.
You can. Okay. All right. Great. I mean, I suppose that's not something that has been explored a great deal, right?
Yeah. Symmetric tensors haven't been explored at all, as far as I know. Yeah.
Okay. Thank you so much.
Okay. I have I think probably a short question about, so is it possible that this U1, at least one of the symmetries becomes, maybe not a dipole symmetry, one of these becomes anomalous, so the normal U1 charge, assuming that the fractons would be made out of bound states of some massless volumes. And so what would be the change in the paradigm? I mean, the fact, because most of the stuff comes from the fact that there's strictly there are these sectors to not fix.
Yeah, it's certainly possible. One of the symmetries could be anomalous. No, it's not something that's been explored. Yeah, so as I said, we're still at the tip of the iceberg here. So somebody should do it. What happens if one of these symmetries is anomalous? Yeah.
Great. Yeah, thanks again for this amazing and very nice introduction to this fractons and of your work on this, covering various aspects of it. And I hope you will visit us in Chennai then, and we can. Okay, so I end the meeting now, but we can still talk a little informally.
Sure.